Day 17. We've got a routing problem. The uh, the essential nature of the problem is we've got this grid, and we are looking for a path through the grid that gets from the top left to the bottom right, I hope. I think it's bottom right. Yes. Uh, is this right? Let me see. Top left city block, the destination, bottom right city block. Okay, great. Because you already start in the top left block, you don't incur that block's heat loss unless you leave that block and then return to it. Okay. I can tell that will have already tripped some people up. Noted. Okay, so our job is to get from the top left to the bottom right, minimizing the total number of cells. That is the cells themselves are numbers, and we are adding the numbers along the way. And we want to find the minimum, the path through that if you add all the numbers together, produces the minimum number of any path through. However, there is one additional quirk, which is that we can't go in a straight line for any more than 3 blocks, after which it must turn left or right. So you can see that here. We've moved once to the right, to the right, and to the right, and then we have to turn again. Plus, the top left doesn't count unless you have to pass through it once more, which I surely not. I mean, that would be surprising. So it's a routing algorithm, I think, with a few quirks in it, which means we should be able to apply A star as long as we are careful about it. We should be able to apply A star. So the A star algorithm, I always forget how on earth it works. So I'm always looking at this. There are uh, a few things to sort of note here. The first is that when we're using A star, typically we're looking for the shortest distance. So interesting. Yeah, we're looking for the shortest distance. So we're often doing something like, I don't know, we want to get, let's forget the keyboard shortcuts for this. How do I do this? Oh, anyway. So we're trying to find this path through, and if we were doing that here, all paths would be the same length, because you either go straight down or straight across, doesn't really matter. So here we are, we're not looking at the distance. We're looking at something else. We're looking at the sum of the numbers along the line, I think. Trying to minimize. Yeah, trying to minimize. Yeah. So A star comes with a few different parameters, a few different things. It's an algorithm that conceptually, to me, you can say it needs a few things, and the implementation of these things is up to you. It needs to be able to find the neighbors of a cell, and it needs to be able to find the cost of I think it is basically a cell to cell hop. it also provides us with the opportunity to use a heuristic, which is our estimate for how long, how costly the path we have yet. What am I trying to say? It allows us to provide an estimate for how costly we believe it is going to be to get to another cell from the cell that we're on. Or rather, it allows us to provide an estimate. Okay, let me give an example. So let's say we're on, let's say we're on this cell, this 3 here, and we can choose whether we want to, in fact, this will be easier. We can choose whether we want to go left, right, up, or down. Now, it would be good, if this was a normal pathfinding problem, it would be good for us to prioritize going to the right or going down. Those would be the paths that we'd like to go on, we'd like to favor, because they get us closer to our goal, which is all the way. Oh my gosh, what a nightmare. Which is all the way down here. We'd like to deprioritize, but not totally discard these cells because they take us further away. So they're unlikely to get us there. They might still if we have to go around an obstacle, but we don't want to pick them first. So we have the opportunity to provide a heuristic. Now, I'm not 100% sure whether the heuristic will be useful here or not, but I do know enough about the A-star algorithm. And what I know is not much, but I do know enough about it to say that it is not going to hurt as long as we follow the rules of what the heuristic has to conform to. So it shouldn't hurt to have it there, and it might help us avoid some processing time. So probably easier to implement it now than to try and shoehorn it in later, is my guess. I mean, I don't know. But I think. So there are some rules for the heuristic function. So actually, to say how we're going to apply this, the heuristic function here, we do want to generally be biasing towards going down and right. Not entirely, because that might be a very expensive path. So we want to also cover the other paths that we could go down. But going down and right is generally a good idea. But we do need to be careful because there is a rule for the heuristic, or not a rule, but we need to, if we want to guarantee that we're going to find the best path through, that's the cheapest path through, and that's our task after all, we need to make sure that the heuristic is what's called admissible. It never overestimates the cost of reaching the goal. So in this case, my initial thought was we should probably make it like 4.5 or something like that, because that's the average of the numbers 1 to 9 or something. I think it is anyway. But that may overestimate the cost of getting to the goal, so it would make the function non-admissible. So this heuristic function, do we have any zeros in here? Small mercies, okay. We don't have any zeros. So we should be saying that the heuristic function should estimate as if each cell is 1 and not above that, because if it's above that, we may get it wrong. Consistency is optional, but good because it makes things more efficient. And it's, I believe what it means, I'm less clear on this, but I believe what it means is the heuristic should, if it is to be consistent, its estimate should always be less than or equal to the estimated distance from any neighboring vertex to the goal plus the cost of reaching that neighbor. So what that means, I believe, don't quote me on this, is that let's say this cell, let's say we're considering these two cells. And the cost of this cell is the cost of the blue cell. Let's say it's 6. It's not 6, but let's say it's 6. Sure, let's make it bigger. Let's make it 100. Oh my gosh. No. Let's make it 100. I really have to find a new diagram tool. Let's make it 100. Now, the heuristic function, I think it is consistent if the estimate of this, of the cost of this cell reaching this cell should be, what is it? Less than or equal to the estimated distance from any neighboring vertex, less the cost of getting to that cell. So in this case, it should be 98 or fewer, I think. In any case, it shouldn't be a big problem for us because we'd have to do something pretty weird to break that rule. Again, I'm not absolutely certain about this, and these points may end up being important, so I may have to become certain of them later. Right. So the heuristic, we need to essentially assume each cell is 1 for the purpose of the heuristic. So it's the Manhattan distance essentially, which is the down cells and the right cells, the down jumps and the right jumps added up. So the heuristic we need to be careful of. The cost we know, and the cost of the cell jump, I believe, should be the cost of the cell that we are going into. So to get from 2 to 4, we should incur a cost of 4. That way we handily cover the requirement that we don't count the 2. Now the neighbors are complicated for a different reason. The neighbors are complicated because the neighbors that we have, now you might think we could go down, this, let's say this 5 has the neighbors 2, 6, 5, and 5. And it can go to any of these neighbors, but it is not true. It can only go to neighbors depending on where it has been before. Just realizing something. Where it has been before. So let's say, let's consider our path. Let's say we've gone this way and I wish I knew what the combination was to add on to it. And then this way. So in this case, we can go, we actually can't do that anyway. Let's say we've come from up here. We've gone 1 down, we've gone 2 down, and we can go another 1 down. So if we're here, we could go left or right, or we could go, in fact, this is going to make things harder, isn't it? Let me choose a different example. Let's imagine we're in here. Let's say we've come from here. We can go any direction, that's fine. Now, if we've come from here, and we've gone down, down, and down, we can now no longer go straight ahead. Because, in fact, can we go back on ourselves? I don't see, yeah, and there's no reason probably we would want to. Yeah, I think we can only go left or right. Yeah, 90 degrees left or right. It also can't reverse direction. Okay, great. So actually, yeah. Now, in this case, we definitely can't even, oh gosh, okay, enough of this. I hate it when it loses the keyboard shortcuts like this. Nope, nope, just no good, just no good. Okay, so even in the case where we've only traveled a couple steps, we definitely can't go back. Now, if we've traveled more steps, we can't even go forward. We've got to go left or right at that point. So it matters where we've come from and how long we've been traveling in that particular direction, which means that our vertices are going to be sort of, we're going to be in a weird space. We're not going to be in this space because we might get to this cell. We can't just say, okay, this cell, from this cell, you can only go left or right, because we don't know where we've come from. If we come from here, and we're on that cell, we're going to be going left or right. Here, here we can go left, right, or forward. So the location in the grid is not a guarantee of what the neighbors are, what the directions we can go. So what I'm wondering now is if we can simplify the problem a little bit and say that, let's say we've got this blue cell. Let's say we've ended up on this. In fact, let's start off here. Now, the neighbors of this cell are this, this, and this. No, that doesn't work, because then we won't know if we can go. We won't know which directions we can go in just by being on the cell. Hmm. Okay, let me continue on this path for a bit. Or this, this, and this. Okay, so it doesn't necessarily make everything a lot easier. We've still got to keep track of a certain amount of information about our position. So our position must in the really is sort of, if we call it position, it's slightly misleading, but think of it as like the state of our sort of cart. We do care about the X and Y. We care about the direction, which is itself an X and Y. Or it could be, I mean, doesn't necessarily have to be, but I like to represent it that way. And then we care about like the cells that it's gone in a particular direction so far. Let's call that track. This allows us to get the neighbors. Okay. Well, I'm worried that this is going to explode a little bit. guess we're going to end up with how many cells? So we've got, I'm just going to look at our input briefly. We've got 142 columns and 142 rows. So we've got 142 cells. We can be in one of 4 directions, and we can have our track be we've gone, well, we must have gone some cells in a particular direction, or at least most of the time. So I mean, 0 in the top left is going to be a special case. But we can have gone 1, 2, or 3. So we've got 3 combinations there. So our total space is 142 times 2 times 142 times 4 times 3. 241,968. 214,968. Quite a lot of cells. Not incomputable, but if we're doing another algorithm on it, we're going to end up with we will only have to calculate the true cost of each cell once. So I think we'll probably be okay, just due to the way the algorithm works. So I think we'll be okay. But it is slightly troubling how big that number's getting. But the approach probably will, let's see. I think probably the best thing to do is to try it. So let's go with neighbors. Let's go with getting the heuristic to and then we've got our grid. Which I think I'm going to have just because it's my favorite approach, a set of cells, which the cells are going to be a pos vector, what is it? What do we call this thing? Heat loss. And then we're going to have our state, which of course is going to have a grid and a part. I'm also going to have definitely going to have a viz. That's going to be important. And a calc min heat loss. I think we won't even need the path, will we? Yeah, it's quite good. Alvec we already know about. We could steal that from last challenge. Okay, so what's our plan? Do we even need? Then we can probably just put this in here. And actually, this can be a bit of effects to, let's go with cell, just in case we need to have him here later. And then we've got our last line and our calculate. We want to verify, what do we want to verify? This we don't. Okay, grid, that. This we want to verify the neighbors heuristic state. Okay, that's good. I'm going to make my screen less orange as well. Ah, lovely. Okay. You also get to watch me ham-fistedly implementing A star, probably getting it incredibly wrong. To pay special attention to that. Maybe I want to model a jump of some kind. No, it can just be a cell, right? Cell can achieve that. Heuristic should be on here. Yeah, I think that's right. Yeah. Okay. Or should it? Yeah, no, I think it should be. Okay. All right. I think this puts us in a reasonably good position. Switching to the code. Okay. Now let's get started. Still that too. Okay. Is it order? Is that what it is? Yep, it is. On my plan on the other computer, hence why I'm looking over there. All right, so this should be the Manhattan distance, which should be 9 plus 9, 18. Yeah, that's exactly what it should be, because we've already incurred the cost of going. Yeah, okay. Let's make this a bit easier to see if it's wrong. Okay. We need to not compare that because we should be comparing based on the, or actually, now I think of it, we should be comparing based on the minimum heuristic, right? Okay, so actually we need to not be ordering based on that. Okay, all right, good to catch that. Say we're at 5, 5 and 5, and the direction we're going is going right, and the track is 1, so we've just gone 1 across. Now the neighbors should be it would be easier if we just made the vectors, I think. Yeah, okay, let's stick with that. Yeah, may live to regret it. Hopefully you'll be okay. So this should be 1 to the right, which is 6, 5. No, yeah, 1 to the right, 1 up, which is 4, 1 down, which is 6, and no going back. Okay. If track is no, wait. It's carts we're creating. So a cart of this position in the direction going right with a track of 2 going up with a track of 1 and then going down with a track of 1. That's what we should be getting. Okay, if the track is, in fact, let's just TDD it and we'll worry about the complexity when it arises. What is that? And then there's if we're going right, we can go up or down. If we're going left, we can go up or down. If we're going up, we can go, okay, fine. Okay. If we're in the verticals, then we can switch direction and go horizontal. With the track now of 1. Or we can do right. And I mean, we probably could just subtract anyway. Okay, that's good. We're going left, it's the same. But we're going back one. So we should be going 4 here. Correct. Now if we're going up, we can go up, we can keep going up, which means we go to 4. We can go left, which we know is 4, 5. Or we can go right, which we know is 6, 5. That's wrong. This is the one, right? Yeah. Okay. So we're expecting, oh, okay, good. And then if we're going down, it's the same, apart from we know down is 5 and 6. So you're good there. Now we need to just check the logic on this. This should be 3 now. And if we're here, we should take this out. It's less than 3. Okay, great. My friend is doing some weird stuff today. Okay, that's that verified and written. That's the cart neighbors now. Let's look at the state. See that? That is not going to be that good. Okay. What was the one from last time? We could probably steal that. And we can steal this too. Okay. Great. We've already verified the off-screen one, so we don't need to verify that again. Now we've got our put that there, and then let's steal this as well. Then let's go with state cells pos equals cell pos, and then it's the int x, isn't it? No, int phone. Okay. And then with this, we want to see if pos in let's still to calculate from here as well. Okay, is this correct? Looks good. Okay. Great, now we're on to the actual work. It's totally cribbing from Wikipedia now. Now, G-score is the cost of the cheapest path from start to end currently known. Okay, I'm going to go with default dict. Now, what is infinity in Python? Okay. That's the G-score. G-score for the, so the end, actually we need to say what the end is. Let me actually triple check this. It's going to be -1, I think. Okay. It should be a cell, right? Let's go with that. Okay. No, this is going to be a dictionary. Great. Okay. And the set, yeah, okay. Okay, we'll do that later. For current neighbors. I know this is the distance, not the age. Yeah, the distance is um the neighbor was equals. Okay, we need to also do this. Get rid of the off-screen ones. Oh, okay. I'm low on battery. Give me a moment. Losing valuable time here. Okay. Okay, now if tentative G-score is less than the G-score of the neighbor cell, okay, then came from this is going to be a dictionary of cell to int float. Hmm. Hmm. Okay. All right. Let's hope that doesn't cause any problems. I guess it makes sense for infinity to be a floating point. Okay. Came from, oh, so fiddly. Okay. Current. What is current? Yes. Current is current is cart. Hmm. Okay. Yeah, the cart is what we're really tracking, annoyingly. Is cart frozen? Yes, it is. Okay, something good in there anyway. The cart has a position, a direction, let's call it going right, doesn't really matter, a zero. And then the end, this is going to be a problem, but probably not that big a problem. If we say that this is a vec, at least that will remind us. Don't need that anymore. That could be that. We can put this on here in the end. Okay, that still works. Now came from is going to be a dictionary of carts, two floats. Okay, that's right. Neighbor to be the tentative G score and the F score to be the tentative G score plus the heuristic function, which is neighbor H dist self end. If neighbor not in open set, which is to check really, then to check add, and this is actually going to be a heap push. Neighbor. No, to check neighbor. We really want to order by the heuristic. That's the tricky part here. Uh, what is it? There we go. No, it's not. That's not unknown at all. Oh, I've just messed up the syntax. Okay, fine. Right. No. Okay. Oh, unhashable type cell. Where are we trying to hash cell? Neighbor cell. This typing is going to be important. Okay. Couldn't find the path. Current pos. Okay, so we got no neighbors, right? We do get here. Uh, do we get here? Yes. If neighbor not in to check, we should be pushing into the to check, right? So we should get here. Oh, this is too indented, that's why. Okay, we're ordering. Shouldn't matter, but okay, we're finding the right path. Good. Okay, now to reconstruct the path. It's taking a while though. It's kind of troubling, isn't it? Path. Now this should be a dictionary of carts to carts. And current should be the okay. Great. Now let's go to this is going to be a list. less the first one, right? Zero. Okay, great. It's empty. It's empty. Okay. 101. A little closer. 102. Okay. Okay. 10, 102. 102. Why is it off by one? Why is it off by one? We do have 00 in there. Well, I know we're supposed to take one off. I don't see how that will help us. We got 99 there. Ugh. Okay. We seem to be going sort of a good direction. I'm not counting the last one. That's why. Okay, now we're good. Let's try with the input. Get rid of this viz for one. Don't need that. So this doesn't take a million years. But it is taking a while. Okay. 1076. Let's try it out. Okay, good. That is a bronze, just about. Well, not just about, comfortably. Okay, the crucibles of lava simply aren't large enough to provide an adequate supply of lava to the machine parts factory. Instead, they're going to upgrade. Even more difficult to steer than normal crucibles. Not only do they have trouble going in a straight line, but they also have trouble turning. Once an ultra crucible starts moving in a direction, it needs to move a minimum of 4 blocks in that direction before it can turn, or even before it can stop at the end. However, it will eventually start to get wobbly. An ultra crucible can move a maximum of 10 blocks without turning. In the above example, an ultra crucible could follow this path to minimize heat loss. In the above example, an ultra crucible will incur the minimum possible heat loss of 94. Okay. Well, all right. So minimum of 4. Maximum of 10. Okay, that doesn't seem too difficult. Are we going to get an explosion of possibilities? I don't think so. Should be even fewer possibilities, right? All we need to do is change our neighbors. And in principle, our neighbors could be simpler anyway, probably. But I don't think we need to make it simpler. So we need to then keep track of the track and then just change the neighbors calculation. And then it does also have to, we have an additional condition for the ending point. Okay. All right. Well, I think this will be okay. I think we can go straight into coding this one. Well, I say that. Let's just give a little effort to planning. Let's say write and verify neighbors and a rule to stop the condition run for a while. Yeah. Let's have a go. Reset the timer. Okay. So now let me actually have it just work on the trial. No, not the, there we go. So minimum of 4 blocks. So that means it can move 1, 2, 3, or 4. So if it's under 4, it can only move in this direction. Otherwise, it can move these directions. So in the case where the self track is less than 10, it can go in any direction. If it's yeah, let me just keep these branches. I think that'll keep things simple. Okay, so if it's below 4, it it can it can only move forward. If it's above 4, if it's 4 or above, um, but under 10, it can go forward, or it can change direction. If it's at 10, it must change direction. Oh, this is going to make it slower actually, because we've just taken up the space by, it's not going to be that much slower, I don't think, but it will be definitely be slower. If it's at 10 and if it's over 10, something's gone wrong. Okay, so let's say here, it's got to be going right. It's got to be going left, up, down. We're there for now. Now, if it's going to, it should be going down. Come on. It's going 3, it should be going down. If it's going 4, at most 3 blocks, a minimum of 4 blocks. So if it's going 4 blocks, it can turn. So at 3, it can't turn. At 4, it can. Or it can turn. Okay. At 5, it can turn 6, it can turn 7, it can turn 8, it can turn 9, it can turn. And then at 10, it must turn. Okay, great. And then let's have one of these and just to make sure I haven't broken anything. Actually, that doesn't make any difference. May need to re-verify that. I'm pretty sure I've got that right. Okay, and this is now at 94. However, we haven't got the ending point yet. Before it can stop at the end. So, and current track has to be four or above. Okay. Good. This is just for me, actually, just to see things. Okay, let's try this with the input. Very slow, isn't it? But it's not ridiculously slow. I think it'll probably be faster if we take down the visualization a bit. Yeah, it's a bit faster now. In any case, faster than me doing some more coding, I think. We may even get it to be platinum. Anyone got any good jokes? Oh, I've got one, but it's a not joke, but you have to start. So how's this one gone? It's gone okay. Yeah, I mean, it could possibly be optimized a bit more. I wonder if there's I mean, to me, it doesn't seem, you could possibly optimize out the neighbor's calculation so that it would either go, so that it would essentially jump at once. That would probably save you a certain amount of work. If I needed to optimize it further, that's probably where I'd start. But I mean, in theory, that shouldn't make any difference, I don't think. Should start speeding up soon, I think, as we get through the first column, first rows. This is going to be really funny if it's not the right answer, isn't it? It's really speeding up now. Hey, what did we get to? 1219. Let's try that. Okay. Well, the power of letting the processor go, I suppose. Probably there's a way to make that more efficient. Maybe it's by making the leaps. Yeah, be kind of curious to figure that out, but that's an answer. See you tomorrow.